Then 1.1, they're asking us to evaluate the sigma of x equals to 3 up to 5. So which means the starting point must be x is 3, and then the last n must be 5. So what we need to do, we need to first of all understand what does the symbol sigma mean. So sigma is more like a shortcut for sum, or sometimes we call it a summation. In other words, you must get the summation of all the terms of all the numbers within this sequence or pattern from x is equal to 3 up to 5. So I need to get that pattern or sequence, and I'll do that by simply replacing or substituting the x with a 3 for me to get the first term. Okay, so this is gonna be 2 times 3 squared minus 3 times 3 plus 1. So that is 9 times 2 is 18, minus 9 is 9 plus 1 is 10. Okay, and then I need my second term, whereby x now is gonna increase to a 4. So 2 times 4 squared minus 3 times 4 plus 1. So that is 16 times 2 is 32 minus 12 is 20 plus 1. It's gonna give us a 21. And then the last term, which is t3, that's where the x is a 5. So it's 2 times 5 squared minus 3 times 5 plus 1. So that's 5 squared is 25 times 2 is 50. 50 minus 15 is a 35 plus 1. I get a 36. Now, since they were telling me to do the sigma or the summation, which means I have to add up all these 3 terms. So that will be 10 plus 21 plus a 36. And then I end up with something like a 67. Okay, that is question 1.1. Then we move on to 1.2. We're being told that the third term of a geometric is 36. The third term of a geometric series is 36. And then the sixth term is this much. They want us to determine the first term and the common ratio. So from the question, I can summarize and say that T3 is a 36, and then T6 is a 777, 6. What do they want us to get? They want us to get the first term, which is the A, and then they want us to get the common ratio R. So we know that since it's a geometric, we need to use the nth term of the geometric, which nth term is Tn is equal to A R exponent n minus 1, whereby A is our first term and then R is our common ratio. So if I was to find the third term from the nth term, it will be like AR 3 minus 1, which is squared, or AR squared. Then I can substitute T3 with the 36. So which means, I don't know, let me just write it like AR squared is equal to 36. I can call this my equation number 1. And then I'll do the same with the T6. So we know that T6 is going to be AR to the exponent of 6 minus 1, which gives us a 5. And then where there is 6, I'll replace the 777, so which means my AR to the exponent of 5 is equal to 777, 6. Then I'll call this equation number 2. And then I have to solve the 2 equations simultaneously. Okay, for as long as it's a geometric, the recommended approach is you divide the 2 equations. Okay, so since this looks to be like the bigger one, I'll say equation 2 divided by equation 1. So it's like AR to the 5 is equal to 777, and then I'm dividing it by AR squared is equal to 36. Okay, so when I divide this, the A's are gonna cancel the A's, and then I'll be left with R cubed. And then if I'm to have 777 divided by 36, my answer is a 216. And then I can either take the cube root, or I can express the 216 with an exponent of 3. or in exponential format. So if I'm to take the cube root, my r is going to be 6. Okay, mind you, the question was asking for the r and the a. So having obtained our common ratio as a 6, we can use equation 1. Okay, so we can say substitute r into equation 1 to find a. So we are saying a, our r is 6 squared is equal to 36. So this will be a 36a is equal to 36. Divide both sides by 36, which means our a is a 1. So the first term of this geometric series is a 1, and then the common ratio will be a 6. Question answered. The next, we have question number 2. They're asking us to consider the figure below. Okay, have some drawings. They're telling us congruent regular hexagons. So congruent simply means these hexagons are the same, they are similar, they are equal to each other. Are arranged as shown in the diagram. The perimeter of one hexagon is 12 units. So we know that perimeter is the total distance that is around any given shape or object. So for a hexagon to have 12 units in perimeter, we need to first of all determine what each side is having before we can go on. So it's 12 divided by 6 sides, which is 2 units. Okay, so which means this is a 2, this is a 2, that is a 2, that is a 2, that's a 2, and inside there we have a 2. Okay, so the question itself is asking us to determine the perimeter of the shape formed by 20 hexagons arranged in this manner. So we have hexagons that are just increasing in that sort of pattern. We don't know how the order is, but we have 20 of them. So one thing we need to look out for, what is happening or what is going on within this question. So if I'm to look at the first hexagon, with the first hexagon, I'm having 1, 2, 3, 4, 5. 5 sides that are independent. And then there's one side that is being shared. So if that is the case, which means even the last hexagon is going to be more or less the same thing, because it will be just attached to one of the hexagons. So one side of it has to be shared. Okay, when I look at the second hexagon, it's like 2 sides are being shared. So it's only 1, 2, 3, and 4 sides that are open. Okay, applies to the third hexagon, 2 sides are being shared, which means 4 sides are open. And then the story continues. So which means for as long as sides are shared, we don't need to double count or double addition. So we shall have to exclude some of the sides. So my approach would be, I would look at, let's say, the first and the last hexagons. The first and the last hexagons, what will be the perimeter? Okay, since we know that the first is having 5 sides that are open, so it's going to be 5 times 2, because each side is 2 units. And then since we're looking at 2 of them, the first and the last, and then I'll multiply this by 2 again. So this is going to give me 20 units since it's perimeter. Okay, then I will look at the middle hexagons or the middle pattern. So with the middle hexagons, how many will they be? Since I've removed 2 out of 20, I'll be left with 18 of them. So with these 18 hexagons, each hexagon is having how many open sides? It's 1, 2, 3, and then 4. 4 sides that are open. But each side is 2 units. So it's 18 times 4 times 2. 18 times 4 times 2. That's going to give me 144 units. Then for me to get the total perimeter, I'm just going to have 144 plus 20, which will give me 164. units. Now remember, for as long as it's perimeter, our point of interest is just the distance that is outside of the shape. The distances that are shared do not count in this case, just outside. Just focus on the outside only. Okay, so 164 becomes our answer. And then 2.2. They are telling us that the diagram shows a number of concentric circles. So concentrics, like circles that are originating from the same center. The radii of the largest three circles are given by 16, 16 over 7, and 16 over root 7, and then 16 over 7 respectively. 2.2.1, they want us to show that the areas of the circles from a converging geometric, or we must show that the areas of the circle form a converging geometric series. So for us to do that, or to show that the areas form converging geometric, we need to remember the condition for convergency, that our common ratio must be between -1 and +1. The common ratio must be between this. Okay, so we've been given the radii, so we need to find the area of the first circle. We know that area of any given shape is given as pi radius squared. So that's going to be pi times 16 squared. And then when I look at the area of the second shape, it's going to be pi again, multiplied by 16 over the square root of 7 squared. So this simplifies itself to pi 16 squared over 7. When I do the same for area number 3, it's going to be pi 16 over 7 squared, which is like pi 16 squared over 49. So if this is my first term, second, and third, because now my focus is just these areas, I need to determine the common ratio. And I know that for me to get the common ratio, I can get T2 divided by T1. So this is going to be pi 16 squared over 7. I'm dividing it, I'll just say times 1 over pi 16 squared, because I'm dividing by pi 16 squared, and then I change the sign to multiplication, which will be that. So this is going to cancel that, and then I'll be left with 1 over 7. Now we know that 1 over 7, when you just change it to a decimal, is 0.142 something, which is in between this condition. So since, okay, we can just draw a conclusion that since -1 is less r is less 1, then the sequence converges or will converge. Sequence converges or will converge since the common ratio is between that interval. Okay, and then we look at 2.2.2. 2.2.2. So from the same question again, they want us to determine the sum to infinity of this series. And then they want us to round off the answer to the nearest whole number. Okay, so we know that from the previous question, our first term was the first area, which is pi 16 squared. Okay, so I'm just gonna jot it down here, and we say that our A, which is T1, is pi 16 squared. Our common ratio, we said it's 1 over 7. And we know that from the formula of sum to infinity, it's A over 1 minus R. Our A is pi 16 squared over 1 minus 1 over 7. So if I put this into my machine, into the calculator, I'll have pi 16 squared 1 minus 1 over 7. And then I'm getting 938,289. And then for me to get the nearest whole number, I just have to round this off, which is approximately 938, because 2 won't affect the 8. That is 2.2.2. And then 2.3. 2.3, consider the sequence, which sequence is having 12. We have 9, there's a 4, there's a -3, and then there's a -12. Consider the sequence, and they're asking us for the nth term. So which nth term is also the rule or the formula? Now, we don't know whether this sequence is arithmetic, we don't know whether it's geometric, and we don't know whether it is quadratic. So we need to first of all test it and see. If we try to do the division, 9 divided by 12, okay, 9 over 12 is gonna give me 3 over 4, okay? What if I try 4 divided by 9? Do I get the same thing? 4 divided by 9, I don't get 3 over 4, which means it's not a geometric, okay? We said 9 over 12 is 3 over 4, and then 4 over 9 is not the same as 3 over 4. So geometric is out. What if we tried arithmetic? We remember arithmetic must have the same constant difference. What is 9 minus 12? That's a -3. Okay, and then 4 minus 9, that's a -5. So still, it's not an arithmetic. So we're just gonna change that. And let's try the last option, which is the quadratic. So we're saying T2 minus T1 must give us our first difference. Okay, so 9 minus 12 is a -3. And then 4 minus 9 is a -5. And then -3 minus 4 is gonna be -7. And then the story continues. -12 minus -3 will give us, what does it give us? -12 minus -3. It's 9, negative. Okay, so we know that this first difference is not the same, it's not constant. So let's try to check the second difference. So -5 minus -3, that's a -2. And then -7 minus -5, which is also -2, which means this is a quadratic sequence. So we know that with a quadratic sequence, the second difference is going to represent our 2a. Okay, second difference is representing 2a. The first term of the first difference is going to represent 3a plus b, and then the first term of the quadratic will represent the an squared plus bn plus c. Is that true? Is that true, guys? No. Is that true, the an squared plus bn plus c? No, it's supposed to be a plus b plus c. Okay, so we know that the general term of a quadratic is the an squared plus bn plus c. Then let's start by finding the value of a. So with the value of a, I'll just get the 2a, and then I'll equate it to the second difference, which is -2. Divide both sides by 2, which means our a is a -1. I'll get this -1 and then substitute it into that second part. So 3a plus b, we said equated to the first term of the first difference. Now if our a is -1, that's 3 times -1 plus a b is equal to -3. I move the b to that side, so I move the -3 that side, so it's -3 plus 3, which is a 0. And then with the first term of the quadratic, a plus b plus c must give me a 12. Okay, but my a is -1, my b is a 0, I'm looking for c. I'll move the one that side because -1 plus 0 is -1. So c becomes 12 plus 1, which is a 13. So having obtained the A, B, and C, all I'm left to do is just do the substitution into this. Where there is A, I'll put a -1. So it's -n squared. And then our B is a 0, so it's just gonna die out. And then the C is a positive 13. So this becomes the nth term or the general rule of that sequence. Okay, then question number 3. Question number 3, this is proportions. Okay, so they're telling us that in the diagram below, triangle ABC and triangle DEF are drawn, with angle A being the same as angle D, and then angle B is the same as E. This angle is the same as this. Okay, and then they're telling us that C is the same as F. Angle C is the same as F, just as indicated. Now, they want us to prove the theorem that says that DE, just write it up here, that DE over AB is the same as DF over AC. DE over that is the same as that. Okay, so what we need to do is do the construction. Okay, we get the big triangle and apply some bit of construction. Let me just make this a bit thicker. Okay, so this has been constructed. We can label this as S and T, or in any other format that you feel comfortable with. Okay, so the first instruction is going to be construct. Okay, we are constructing ST. So with S to be on AB, and then T on AC, such that we know that our AS must be the same as the DE. Okay, and the AT must be the same as the DF. Okay, so that's gonna be the first kind of statement we make. Then if the construction has been made, and remember our condition, we are saying this must be the same as this, and then this has to be the same as that. So we go down and say that from triangle, just make this a little bit big. We're saying that from the triangle, not gonna be able to see. Okay, so from triangle AST, this triangle here, and then the counterpart, which is DEF. Okay, what can we observe that will be the same? So we said AS, the side AS is going to be the same as side DE. The reason we give is that we did the construction. Okay, then same applies to AT, being the same as DF is through construction. Okay, and then lastly, originally they told us that angle A is the same as angle D, so this is given to us. So we have 3 fundamental facts that pin the triangles to be congruent. So you can say, therefore, AST is congruent to DEF. And the reasons are because we're talking of the side, as well as the angle. Okay. And then from there, we need to know that if this angle here is labeled as, let's say, S1, this angle is going to be the same as this angle E. Okay, so it's saying S1 is the same as this E. The reason for that, the triangles are congruent still, so that is congruency. Then let me just erase the top part here, just to create more space. Okay, so triangles are congruent, which means those angles are the same. And then on top of that, we were told that angle E is the same as angle B. Remember, initially in the original statement. Okay, so we can as well equate this whole thing to a B of S1 and E being the same as a B. Okay, now for as long as S1 is the same as this angle B, it simply makes ST and BC to be parallel. Okay, it creates parallel lines. So we can say, therefore, it's a continuation, ST is parallel to BC. What type of angles are S1 and B? Those are corresponding angles. Angles that are corresponding must always be equal. Okay, then having proved all of that, then we can apply our principles of proportionality and say that if we get the AS, we divide it by the AB, it should be the same as someone that gets AT and then divides it by the AC, the big triangle. Okay, but what reason are you gonna give? We're saying line that is parallel to one side of a triangle. One side of a triangle. But we said that DE is the same as AS. Where there is AS, I can just replace it with DE. So DE over AB is the same as, remember we said AT is the same as DF. So that I'm gonna say DF over, excuse me, I'm saying it's DF, okay, over the same AC. Okay, and that's what the question wanted. Prove that this is the same. So all that has to be shown for you to obtain your 6 marks. Okay, reason for the last part could be construction. We did the construction and then we proved that. Okay, so that is question number 3.1. That's question 3.1. Then question 3.2, with question 3.2, we're being told that in the figure below, ABC is a tangent. Okay, still Euclidean geometry. ABC is a tangent. We know the tangent is just a line that touches the circle at one point. Okay, to the circle at B. AB is the same as BC. AB is the same as BC. AB is the same as BC. Okay, so AB is same as BC, already indicated for us, and then BP is a diameter. BP is a diameter. Let's just see that. Okay, just make it a little bit smaller. And then AP is gonna meet, where's the AP? This is AP, meet the circle at point Q. Okay, so this is meant to be a P. CRS is parallel. CRS is parallel to this. Okay, that's been indicated for us. All right. Then step number 1, or question number 1, they want us to prove that triangle. They want us to prove that triangle is similar to the other one. Triangle BCR is the same as triangle SPR. Sorry, is similar to SPR. So when triangles are similar, sizes may differ, but then there are properties that are the same. That's the sides being in proportion and the angles being exactly the same. Okay, so let me just highlight those triangles. They said BCR. This is a B, this is a C, this is R. Okay, so we're focusing on this triangle. Okay, and then there's another triangle that we need to focus on. I'll just highlight it in red, SPR. Is S, where is P, where is R? Okay, so this triangle here. So you must prove that the two are basically similar. In other words, that they have identical angles, since we don't have any dimensions to do with the lengths and stuff. Okay, so what I'm gonna do is I need to look for what is common within these triangles, within this and then within that. Okay, first things first. I know that angle R3, this angle and this angle are going to be the same. So R3 is the same as R1. And the reason we give for that, those are vertically opposite angles. Okay, vertically opposite angles will be the same. So this is fact number 1 being identified. And then since they told us that ABC is a tangent, ABC is a tangent, is it possible for us to create a tan chord? We can see that B3, okay, B3 is going to be the same as Q2. Okay, that's gonna be the same as that. So we can say that B3 is the same as Q2, and the reason is the tan chord theorem. But we know that QB and SC are parallel, which means this Q2 must be the same as this S2. Okay, reason, those are corresponding angles because QB is parallel to SC. Okay, those are corresponding angles. And if that is true, which means that our B3 is the same as the S2. Okay, so for as long as we have two angles known, automatically the third angle or the third angles have to be the same. So you can say P is the same as C. Angle P will be the same as angle C. Sometimes we say the remaining angle of a triangle or the third angle of a triangle, third angles of a triangle. So we have 3 facts. Okay, this is fact number 1, fact number 2, and then fact number 3. So for as long as those 3 facts have been identified, then we can just draw the conclusion that therefore triangle BCR is similar to triangle SPR. Reason, we were focusing on the angles only. Angle, angle, angle. So that's how the 5 marks would be obtained. Okay. And then 3.2.2. 3.2.2. They are asking us to prove that 2RB times SP is the same as SR times CA. Okay, 2RB times SP is that and that and that. So from what we have observed, or from what we have identified in the first question, we can say that if we get a BC, we divide it by SP. Remember, these triangles are more or less the same. So if I were to draw just the sketches of them, this is R3. Okay, this is B3. I'm sorry for the way I'm putting it, but then this is a C. And then if I'm to draw exactly the same thing, to something like that. So it said B3 is the same as S2, and then R3 is the same as R1, and then this is going to be a P. Okay, then I can do the comparison of the sides. So I'm saying if I get my BC and then I divide it by my SP using corresponding sides, it will be the same as someone that gets BR and then divides it with SR. Okay, so this length and this length, this one with that one. Okay, reason for that is that angles that are parallel within the triangles, or it's basically the similarity kind of thing, or the angles that are proportion. It's fine, proportionality theorem. Then from there, we know that BC is a half of AC. That BC is a half of AC. They told us that the sides are equal. So what this gives us, therefore, is that if we have our AC divided by 2 SP, is going to be the same. Remember, our AC now, we are replacing BC with the AC because we know BC is a half AC, so it's just that. It's equal to just the same thing, BR over SR. Okay, then we do the cross multiplication. So if we cross multiply, we know that our AC times SR is the same as 2 times BR times SP, which is just the same thing as what they gave us. So that means I can just rewrite it and say 2RB times SP is the same as SR times CA, just moving it around. So that is how I would have worked that out. Okay, that's what the question asked for. Okay, then 3.2.3. Okay, they are telling us that what if BR, or the ratio of BR to RP, is 2 to 3? What if the ratio of BR to RP is 2 to 3? Calculate the ratio of AQ to QP. Calculate the ratio of AQ to PQ. Okay, I'll just go back to the question. AQ to PQ. So they want us to look at AQ and then PQ. The question was telling us that, let me just change this to a green. Okay. BR to RP. BR, where is BR? From here up to here is a 2. And then RP from here up to here is a 3. Okay. So what are we going to do? So we know that if we say BR over RP is being given as 2 over 3, the reason It's given to us. What if we compare QS from here and then SP also? If I decide to focus on the triangle QBP, so that is going to be QS divided by my SP. QS divided by the SP is the same as BR divided by my RP. But since I don't know the measurements, I can just use the letter X probably. So that will be like 2X over 3X. And the reason is going to be the proportionality theorem for a line is parallel to one side, oh Lord, of a triangle. So line parallel to one side of a triangle, because these were parallel lines. So automatically the proportionality theorem does apply. Okay, then from there we know, I'm just gonna drag this down. Okay, but if I go there, if I decide to compare AQ I'm looking at AQ together with SQ, must go hand in hand with AB and BC. Okay, so let me just jot it down here and say that my AQ, I'll say, but if I have AQ over QS or SQ, it should be the same also as someone getting the AB divided it by the BC. Someone will ask now, which triangle are you using to draw that assumption? So I'm focusing on triangle ACS, this one, since these two lines are still parallel. So I'm focusing on the AQ over the SQ is equal to the AB over the BC over the BC. So reason is still the same thing, proportionality theorem, the line parallel to one side of a triangle. Okay, then if that is true, which means the ratio of AQ to QS is going to be 1:1. Reason being, we know that AB is the same as BC, which means the dimensions are the same or the distances are the same. So that ratio is 1/1. Let me just go down and say, I'm just gonna write it down there for the sake of space. Okay, then I'll say that if my AQ over my QS is equal to 1/1, reason is going to be AB is equal to BC, which was given to us. Which means our AQ over the QS, that was 2x over the 3x. 2x over the 3x can be also multiplied by just the same thing. Just cancel that out. Is it canceling it out? Nope. Let me just erase this. Just erase that. We're saying AQ over QS is also going to be 2x over 2x, since the ratio is 1/1. Which means, or hence, our AQ over the QP, AQ over the QP, AQ over the QP, because we said AQ is 2x, and even the QS is 2x, since these two are equal. So how many x's are we going to have for QP? From our first part, we said RP is the same as SP. from here up to here. So which means this is a 3x as well. Okay, so it's 2 is to 5. Okay, so I'm just gonna say our AQ is 2x over 5x. Therefore, if I cancel out my x's, the ratio of AQ over QP is 2 over 5, or I can say AQ to QP is the same as 2 is to 5. Okay, then question number 4, they want us to rewrite the statement, which statement tells us that a line drawn intersecting two sides of a triangle is equal to the third side. A line drawn parallel to that. And so how do we rewrite this whole statement to make it valid? We know that a line that is drawn parallel to one side of a circle, parallel to one side of a triangle, not a circle, guys. The one side of a triangle, that line must divide the other two sides, within the same proportion. So that is how the writing was meant to be done. So now the statement is valid because the line intersecting two sides of a triangle is equal to the third side. So a line drawn parallel to one side of a triangle will divide the other two sides within the same sort of proportion. Okay, and then with the next question, 4.2, telling us that in the diagram, AC is a diameter, okay, of the circle ABC, and then CG bisects the angle AC, so which means this angle is the same as that angle, and GF is perpendicular. GF is perpendicular to AC, which means it makes a 90. And then CG is parallel to DA. DA and CG, they are parallel. That has been indicated for us. They want us to prove that ABC, that this triangle is an isosceles triangle. So one thing we know about an isosceles triangle is that two sides have to be equal, but also the opposite angles must be equal. In other words, is that theorem that says the angles opposite equal sides. So if the sides are equal, which means the angles must also be equal. Okay, so how do we prove that ABC is isosceles? What do we know from what has been given? There's a diameter, some things are bisecting, and so on and so forth. Do we have any parallel lines? Yes, we have parallel lines. So how do we make use of the parallel lines? So you can say that A1, okay, it's going to be the same as C2. This angle is the same as this angle. Okay, so I'll say A1 is the same as C2. Reason, those are alternate angles because the side AD is parallel to CG. Okay, but we know that C2 and C3 are the same. Okay, that was given to us in the statement where they talked about bisecting, where they said CG bisects this angle. It means those two angles are equal. So if they are bisecting, which means our A1 is the same as the C3. Okay, A1 is the same as the C3. Okay, then now we're saying C3 is going to be the same as D. Okay, we're saying C3 is going to be the same as D. C3 is going to be the same as D. This question is not making sense. We can't prove ABC because this is here. Question is meant to read ABD. Prove that. Is that even true? No. Prove that ACD, not ABC. Okay, no, it's fine. Let's continue. So it's saying C3 is going to be the same as D because we know that those are corresponding angles, because the same lines AD will be parallel to CG. Okay, so if that is true, we know that this angle was the same as this angle, but the same as this angle as well. So which means it's ABC, that is an isosceles, not the other way around. Okay, and the reason is going to be the sides that are opposite equal angles. So which means the length AC is the same as the length CD. Okay, so that is 4.2.1. And then 4.2.2, they want us to prove that BC over that is equal to that over that. So from the proportionality theorem, so I'm gonna just write this side. Okay, so we said this was ABC or ACD. Okay, from the proportionality theorem, we know that BC, is it BC? Nice, BG. BG is where the parallel lines, these are the parallel lines. Okay, so the BG over the GA must be the same as BC, okay, over CD. BC over CD. So in other words, we say that if we focus on this, and then this is our parallel line. So this over that must be the same as this over all of that. Okay. And the reason is going to be line parallel to one side of a triangle, which means AB is parallel to that. But we know that our CD is the same as the AC. The reason that's going to be sides that are opposite, because CD is going to be the same as the AC. We just proved that it's an isosceles triangle. So for as long as the sides are the same, which means instead of us using the CD, we can just use the AC. So it's going to be BG over GA. It must be the same as BC over AC. So where the CD can replace the AC. And then that is proved. That is for 4.2.2. Okay, then 4.3. 4.3. If BC is 12 units, if BC is 12 units, if BC is 12 units, so from here up to here is 12 units. And then they are telling us that the radius is 10 units. The radius is 10 units. Let's say, remember this was a diameter, so if this is probably our circle, can make this a 10. Okay. So one thing we know, if this is a circle and this was a diameter, this angle here has to be a 90, because those are angles in a triangle. Question wants us to get AB, the distance this side. So if it is a 90, automatically this becomes a right angle triangle. This 10 and that 10 will give us the hypotenuse. Okay. So from that triangle, we have a 10 and a 10, which is a 20, and then that's a 12. Let's say that is our AB that we need to find. It's AB. Let's see. Is that what they said? Call this A. Call this C. Call this a B. This is 12. They want us to get, I'm switching it around, guys. The diameter is AC, if I'm correct. Okay. Diameter is the AC. So saying this is AC. And then this is B. Okay, so this is what we need. So from your Pythagoras theorem, we know that AB is going to be the same as AC squared minus the BC squared under square root. Just put it there, because it's meant to be AB squared. Okay, so that's the square root of 20 squared minus 12 squared. And then what do I get? 256. Square root of 256 is 16 units. Okay, so which means the distance of AB is 16 units. And then 2, they want us to get the length of AG. Where is AG? So from here up to here. So if this is 16, we need to find this shorting one. So you can still use that proportionality theorem of ours that we discussed in the previous part, okay, where we were looking at BG over GA, and then yeah, we can compare it in that format. I think that will be quicker and a little bit easier. Okay, so what I'll do, I'm just going to say that if I have my AG over AD, it should be the same as my DC over BD. I'm saying AG over AB is the same as DC. Okay, from here up to here, being the same as that. Okay, so we know that our AG is what we need, but our AB that we got is a 16. Our DC is a 20, because we just looked at it, because we say this side is the same as that side from the first part that we're proving. So it's a 20 over BD. Where is BD? The distance from here out here. So 20 plus 12 is a 32. Okay, so just to write it down and say AG over 16 is equal to 20 over 32. I cross multiply, which means my AG is 20 over 32 times 16. And that gives me 10 units. Okay, question number 5 that talks about some bits of trig. Question 5 to do with trig. We're being told that if the sine 61 degrees is equal to the root of m, they want us to determine the following in terms of m. Now, in most cases, for such questions, we advise people to just draw, even if it's just a small sketch of a right angled triangle. Okay, so if that is our 90, and let's say this is our 61. Okay, telling us that the sine is root m over 1, and we know that sine is opposite over hypotenuse. So it's root m, and that is the 1. For us to get this missing side, can use our Pythagoras. That will be 1 squared minus the square of this and the square root. So it's just the square root of 1 minus m. Okay, 1 squared minus root m squared and the square root for us to get this missing side. So now our triangle is complete. We can go ahead and work this out. So we look at the 241 from your cast diagram and your reductions. 241 is within the third quadrant, which third quadrant has a rule of 180 plus. So which angle do I add to 180 to give me 241? It's going to be 61. And then when I reduce this, I know that sine within the third quadrant is negative. So it's going to be negative sine 61. But I know that the sine of 61 is root m. So this is going to be negative root m. Okay, 5.1.2, they want us to get the cos of 61. So cos, we know, is adjacent over hypotenuse. So our adjacent is this. Okay, this root 1 minus m. The hypotenuse is a 1. So that's going to be just the root of 1 minus m over 1, which is the same thing as root 1 minus m. Okay. Then 5.1.3. 5.1.3, they're looking at the cos of 7.3, the cos of 4.4, and then the cos of the sine of 7.3, and then the sine of 4.4. So when we look at our compound angles, if it's a cos plus sine, which means it's the same as the cos of 7.3 minus the 44. If this was our A and then that's our B, it will be just that. So we know that 7.3 minus 4.4 is going to give us a 29. So it's the same as the cos of a 29. But from this triangle of ours, if one angle is 61, there is a 90. automatically that becomes a 29, the remaining angle within that right angle triangle. So they want us to get the cos of 29. So with the cos, this is going to be our adjacent, and then the hypotenuse is going to stay the same. So that's going to be just the root of m over 1. Okay, because we know that cos of 29 is the same as the sine of 61 and all of that. They are complementary angles. Okay, so that is 5.1.3. Then 5.2, they want us to prove the identity. Prove the identity, cos 2x minus 1 over sine 2x minus tan x is equal to negative 2 tan x. Okay. So it's always advisable to start from a side that is having more terms or more information, and you work towards getting to the side that is having less information. So how can I express this sine 2x, sorry, the cos 2x? Remember, there are 3 ways of doing that, but I'll choose the one of the sine. So this cos 2x is the same as 1 minus 2 sine squared x. Remember, there is also that approach of 2 cos squared x minus 1. And there's also that cos squared x, which is cos squared x is a plus, x minus sine squared x. So from these 3, you can choose any that you want to use. Remember, the right hand side is only the tan. Okay, so for as long as it's like that, I'm just gonna change this. I think I can go with this second one and say 1 minus the 2 sine squared x minus 1. I'm gonna divide this. I know that this identity of sine 2x is the same as 2 sine x cos x. I'm subtracting tan. I'm gonna change this tan into the sine x over the cos x. Okay, when I simplify what is on top here, this one is gonna cancel this one, and then I'm just left with a negative 2 sine squared. So 1 sine squared is gonna cancel this 1 sine x. So 1 sine x will cancel 1 sine x, and then the 2 will also cancel the 2. So I'm only gonna be left with negative sine x over the cos x, and I'm subtracting the sine x over the cos 2x. Oh, there was no need of even me converting that. It's okay. It's fine because I see it's still a tan. I can change this to a negative tan x minus tan x, which gives me negative 2 tan x, and then I'm done. So I've just proved that the whole of the left hand side is equal to the right hand side. Okay, that's quite easily done. Okay, then if I look at 5.4, they want me to simplify without using a calculator. So with this, still it's a combination of reduction formulas and all of that. Okay, for 7 marks. Now with these ones with the alphas, we're gonna express them as reductions and stuff. And then with these ones with numbers like 2 to 5, then we just have to use the special triangles with those special ratios. Okay, let's see. I'm just gonna expand this. So that is a sine 360 minus alpha times the cos of 90 plus alpha. And then I know that 225 is in quadrant number 3, which is 180 plus 45. And then I'm dividing this. I know that it's going to be 1 minus the cos squared of negative. Oh, it's okay. can put this in brackets. Then let me reduce in the next step. I know that 360 minus is in the fourth quadrant. In the fourth quadrant, the sign is negative. So that's a negative sine alpha. Then the cos of 90 plus, these are complementary angles if it has a 90. So that's going to be negative sine alpha. And then the tan within the third quadrant is positive. Okay, so that is tan 45. And then I'm dividing this by 1 minus the cos of a negative angle is the same as the cos of a positive angle. So that will just stay the same as 1 minus cos squared alpha. Okay, then I can simplify what is on top. You know that a negative and negative will give me a positive because I'm multiplying. So that's positive sine squared x times the 1. Okay, because tan of 45 is a 1. And then I know that 1 minus cos squared from this identity of sine squared, let's say x plus cos squared x is equal to 1. 1 minus is going to give me the sine squared alpha. What's wrong with x? It's alpha. Okay, so that and that is a 1. Then I'll cancel that. Everything is just going to reduce to a 1. So this will be my final answer. And that is how I would have approached this paper. All right, guys, thank you very much. Let's meet in the next episode. Hello and welcome to this episode where we shall be discussing more of the revision of the term 1 topics in mathematics. Okay, in the first question, we've been given 1.1. They're asking us to evaluate the sigma of x equals to 3 up to 5. So which means the starting point must be x is 3, and then the last n must be a 5. So what we need to do, we need to first of all understand what does the symbol sigma mean. So sigma is more like a shortcut for sum, or sometimes we call it a summation. In other words, you must get the summation of all the terms of all the numbers within this sequence or pattern from x is equal to 3 up to 5. So I need to get that pattern or sequence, and I'll do that by simply replacing or substituting the x with a 3 for me to get the first term. Okay, so this is going to be 2 times 3 squared minus 3 times 3 plus 1. So that is 9 times 2 is 18, minus 9 is 9 plus 1 is 10. Okay, and then I need my second